Hello everyone, welcome to my YouTube channel. In this video, I am going to explain Wien-Bridge oscillator analysis. So just observe this circuit diagram. So here Wien-Bridge is a feedback network and Q1 and Q2 are the transistors. In this circuit, two transistor amplifiers are used to produce 360 degrees phase shift. So in this video, I will focus on only analysis part. Here, just observe the Wien bridge. One series combination of resistance and capacitance. This is the parallel combination of resistor and capacitor R2 C2. These are the two resistance. Here, just observe the connections. The output of the circuit is connected to the series combination of R1 and C1, and the voltage across parallel combination, that is feedback voltage, is applied to the input of the first transistor, that means base of the first transistor. Okay, now coming to the analysis, so just first observe the Wien bridge construction. So it is the parallel series combination of resistor and capacitor C1 and R1, and one parallel combination of resistor and capacitor R2 and C2, and two more resistors R3 and R4, R3 and R4. So this is the series combination ZS. This is the parallel combination ZB. So just observe the circuit diagram. Output voltage V0 is connected to the series combination, and voltage across parallel combination is applied to the input of first transistor, that is nothing but feedback voltage. So I will redraw the circuit. So this is the series combination and this is the parallel combination ZS and ZB. So here output voltage V0 is connected to the ZS. Voltage across parallel combination of R1 and C1 is the VF, feedback voltage. Feedback voltage. So this is the basic logic. So according to the voltage division theorem, voltage across ZP, that is equal to VF. So VF is equal to V0 into ZP divided by ZP plus ZS. ZP plus ZS. So voltage across parallel combination of R2 and C2 is nothing but feedback voltage. So VF is equal to V0 into ZP divided by ZP plus ZS. So VF divided by V0, that is equal to beta, that is equal to ZP divided by ZP plus ZS. Okay, so this is the basic equation. And what is ZP? So ZP is the parallel combination of resistor R2 and capacitor C2. So R2 is parallel with C2. So R2 divided by J omega C2 and R2 plus 1 by J omega C2. So we'll get R2 by J omega C2 R2 plus 1. So this is the ZP equation. This is the ZP equation. This is the ZP. Okay. Parallel combination. Now coming to the ZS. So ZS is the series combination of resistor R1 and capacitor C1. So therefore R1 plus 1 by J omega C1. Finally we'll get J omega C1 R1 plus 1 divided by j omega c1. Simple LCM. So this is the ZS. This is the ZS. So this equation is nothing but ZS. So ZS. Now the beta is equal to what is the beta value? ZP. So beta is equal to Vf by V naught, that is equal to Zp divided by Zp plus Zs. So we have to substitute the values in this equation. So Zp is equal to what is Zp? R2 divided by 1 plus j omega C2 R2. So R2 divided by 1 plus j omega C2 R2. This is Zp, and Zp by divided by Zp plus Zs. So Zp is equal to R2 1 divided by 1 plus j omega C2 R2 plus Zs. What is Zs value? Series combination of R1 and C1. So already this value is Zs value. So 1 plus j omega C1 R1 divided by j omega C. 1 plus j omega C1 R1 divided by j omega C1. So this is equal to beta. So how to solve this value? Sorry, how to solve this equation? So first we have to solve denominator. Okay. So in denominator, what is the LCM of these two? 1 plus j omega C2 R2 into j omega C1. So this is the cross multiplication. So j omega C1 R2. Okay, again cross multiplication, these two values. So 1 into 1 plus and 1 into j omega C2 R2 and j omega C1 R1 into 1, that is equal to j omega C1 R1 and j omega C1 R1 into j omega C2 R2. J into j square, that is equal to minus omega square R1 R2 C1 C2 C1 C2. So this is the denominator. Now coming to the numerator, direct value, you will get R2 divided by 1 plus j omega C2 and R. So this 1 plus j omega C2 into R2 and this 1 plus j omega C2 into R2 is cancelled. So finally we'll get R2 R2 divided by R2 divided by j omega C1 R1 plus j omega C1 R2 R2 divided by j omega C1 R1 plus j omega C1 R2 j omega C1 R2 j omega C1 R2 plus 1 plus 1 plus j omega C2 R2 1 plus j omega C2 R2 j omega C2 R2 minus omega square C1 C2 R1 R2, and finally numerator value also changes because of this j omega C1. Numerator value also changes. So numerator is equal to j omega C1 R2. So j omega C1 R2. So this is about beta. This is about beta. Okay. By simplifying this equation, we'll get this equation. This is equal to beta. But to produce sustained oscillations, so condition is condition is mod of A beta is equal to 1. To produce sustained oscillations, mod of A beta is equal to 1. So this is multiplied with simply A and multiplied with A. So equating to 1 to produce sustained oscillations. So 1 divided by 1, simple cross multiplications, this value will get j omega C1 R1 plus j omega C1 R2 plus 1 plus j omega C2 R2 minus omega square R1 R2 C1 C2 is equal to a j omega C1 R2. Simple cross multiplication. So equating the equating the real terms, equating the real terms. So what is real terms? So these are the real terms, these are the real terms. So equating the real terms, simply 1 minus omega square r1 r2 c1 c2 is equal to 0. And equating the real terms equal to 0, we'll get this value. So omega square r1 r2 c1 c2 is equal to 1. So omega square is equal to 1 divided by r1 r2 c1 c2. So omega square is equal to 1 divided by r1 r2 c1 c2. So assume r1 is equal to r2 is equal to r, c1 is equal to c2 is equal to c. Therefore omega square is equal to 1 by r square c square. Obviously omega is equal to 1 by rc, and substitute the value of omega formula. Substitute the formula, 2 pi f is equal to 1 divided by RC. Finally, we'll get f is equal to 1 divided by 2 pi RC. This is the frequency of oscillations in Wien bridge oscillator circuit. Now, what happens if we equating the imaginary terms? So just observe this equation, and imaginary terms ni మనం జీరోకి ఈక్వల్ చేస్తే ఏం జరుగుతుంది? Assume R1 is equal to C1 is equal to, R1 is equal to R2 is equal to R. So this is R. C1 is equal to C2 is equal to C. So this is C. So this is C. This is R. So this is C. This is R. So finally we'll get j omega CR plus j omega CR plus j omega CR. That is equal to 3j omega CR and one more imaginary term, that is equal to ja omega CR. So 3j omega CR, 3j omega CR is equal to a j omega CR. Just observe this equation. So assume R1 is equal to R2 is equal to R, C1 is equal to C2 is equal to C. So we'll get 1 j omega CR, 2 j omega CR, 3 j omega CR. That is equal to a j omega CR. So here j cancel and omega CR and omega CR cancel. So amplifier gain must be equal to 3. So, and the frequency of oscillation f is equal to 1 divided by 2 by RC. Thank you.